Hi guys, I'm just going to go over some notes for you real quick that are in your book. So on page 80, you're going to be reading about the history of the atom and how we haven't actually seen what an atom looks like. And so they use the electron microscope to see them. I was just going to kind of explain what that looks like in simple terms. So they have this beam of electrons and they put the sample on a plate, and the sample is coated with gold, and they shoot the electron beam at the sample, and then it's going to kind of the electrons bounce off of the sample because it's coated with gold, and then these secondary electrons that are coming off, they are what produce the image. So then the scientists can use the secondary electrons and a computer with math to calculate a 3D image of what the atoms look like. So we haven't actually seen the atoms, but we're using math to kind of infer what they look like. Okay, sorry for my low technology here. So about 2,500 years ago, there was a man, Democritus, okay, and he had a theory about atoms. He thought that if you cut up a grape and cut it smaller into smaller and smaller and smaller pieces, eventually you would end up with something that couldn't be cut any smaller, and um, he called the uncuttable piece atomos, which is where our atom theory actually originally comes from. But back then, they didn't use scientific experimentation, and so they actually debated science. And so this guy Aristotle, 100 years later, came up with his debate that no, there's no atoms, and he came up with this view of matter that there's four different kinds: air, fire, earth, and water, and that they can be transferred between each other based on if they're hot or dry or wet or cold. And he was incorrect, but because he was arguing this so well, people believed him. So this idea kind of went on until the late 1700s. Now, your book does say that much of the scientific and philosophical knowledge of the Greeks was lost and rediscovered during the Renaissance, and this is actually factually not true. Aristotle's work was discussed by other scientists during that time. Leonardo da Vinci in the 1400s, Copernicus, Thomas Aquinas, so many other people had been talking about this. It didn't just go away, which is what your book states. So that's actually an error in your book. So anyway, then this guy, Dalton, comes on the scene in 1808. And he comes up with the atomic theory. And your book goes through it and it talks about what he proposed. And it seems actually pretty accurate. So on page 82, it talks about all matter is made of particles called atoms. They can't be divided into smaller particles. They can't be created or destroyed. All atoms of the same element are identical in mass and properties, and the atoms of different elements have different masses and properties. Atoms of two or more different elements join together to form compounds in chemical reactions. This guy was smart. Chemical reactions rearrange the atoms, but in specific compounds, the atoms of the different elements always combine in the same way. He came up with the law of conservation of mass, which basically states that matter cannot be created or destroyed, but it can change forms. And this is cool because this is also what happens with energy. Energy cannot be created or destroyed. It can just change forms. So this conservation of mass can be seen when we break down H2O water molecules, and it becomes two separate gases, so the hydrogen gas and the oxygen gas, and they're actually in proportion, because if you notice here, this is two hydrogens to one oxygen atom, and so when the gas is coming out, you're actually going to have twice as much hydrogen gas as you are oxygen gas, but the mass is still there. All that mass remains the same after the chemical reaction happens. So then in 1897, a guy, J.J. Thomson, he creates this experiment using electricity. And at the time, they thought that electricity was positively charged. So he puts the electricity through his device that he created, it goes through this plate here. And when it gets to the plate, it's actually, let's see if I can show you this. It deflects away from the positive, kind of down, sorry, I said that wrong. It deflects away from the negative, okay? Because if you have a negative and a negative, they are like charges and they want to repel away from each other, right? So it's attracted towards the positive here, because if you have positive and a negative, they are attracted to each other. So he basically discovered that the electrical current was negatively charged and that all matter has negatively charged particles. And that's what he saw with the beam. So he came up with this model of matter, and knowing that there were negative charges, he thought that they were dispersed all throughout the matter, and it's called the plum pudding model. So I think it shows in your book a picture of a muffin with blueberries all throughout, and that's kind of what he was thinking that the molecules were looking like. So then in 1899, this guy Rutherford, who was studying under Thomson, came up with the gold foil experiment. So basically he took the helium molecules, and usually there's electrons. Sorry, that's negative electrons around here. So he removed the electrons, creating this positively charged atom, and he filled his box with the positive charges, source of alpha particles is what your book says. Okay, he's got thin gold foil right here, and then around it he puts a zinc sulfide screen that can detect the scattered particles, so it kind of has like a reaction that he can see that the alpha particles are reacting here, so we know they're over here, or they're over here, or they're over here. Okay, so he shoots his beam of alpha particles positively charged at the foil, and what he sees is that most of them are going through, but some of them are deflecting off at really large angles. Most of them are going through, some of them are deflecting off. So because of this experiment, he was able to infer this new model of the molecule, or rather the atom. Right here, there's a dense middle, he found out, because as he's shooting the alpha particles at it, so remember the alpha particles are positively charged, and you've got proteins in the middle of the nucleus of an atom that are positively charged, okay? And so some of these are repelled, and so they're bouncing off, okay? The majority of his beam was going through the foil, and so he decided that that must mean that most of the atom is empty space, okay? But right in the middle was this dense spot that was reflecting the alpha particles. So that's how he came up with, oh, there must be something, some dense middle in the middle of the atom. So here's Rutherford's model that he came up with the positively charged nucleus and the electrons orbiting around the nucleus. And then eventually this was changed to show that the nucleus, his experiment only showed the positively charged protons, and he didn't know that there were neutrons in the nucleus. So now we know that there's the positively charged protons, and then there's also the neutral neutrons in the middle of the atom. Okay, so this is basically what the atom looks like. So you've got your protons that are positively charged, and there's two protons in this one that I'm drawing. So if you look at your periodic table on page 534, you see the periodic table of elements. You see hydrogen is the first one, and then helium is over here with an atomic number of 2. The atomic number comes from the number of protons in the atom. Okay, so this is helium. He, and by the way, a lot of the elements on the periodic table are going to have things that don't really make sense, like iron is Fe, and that's just because it comes from a Latin word, so a lot of them are just Latin based, so they might not make sense, but helium does because it's He. So helium has 2 protons. I'll just put a little 2 here. Okay, It's the second element on the periodic table, and the protons are what tell you what kind of element it is. So 2 protons in the middle, and then we have 2 neutrons. So these are just neutral, they do not have a charge. And then around that is going to be 2 negatively charged electrons. Because when this molecule is happy and all its energy levels are filled, it has just a neutral charge, okay? So you have to have them balanced out, negative, positive, and then negative, positive. So they kind of match there. And then these guys don't have any charge. The neutrons are neutral. The protons are positive. The electrons are negative. Okay, so that's your basic atom. So remember, the atomic number comes from the number of protons in the atom. So this is a helium atom, and it has 2 protons, so its atomic number is 2. When we talk about the mass number, that's a little different, and that's the sum of the protons and the neutrons in the nucleus of the atom. And so what would this mass number be for helium? 1, 2, 3, 4. The mass number for helium would be 4. So if you go back to page 534, sorry, I think my camera flopped itself over. So if you go to page 534, where you have your periodic table of elements, and you find helium, you can see right there the atomic number is 2. It has 2 protons, and the mass number is 4. Okay, so then let me just mention isotopes. So isotopes, atoms of an element with the same number of protons, but different numbers of neutrons. So if you change the number of protons, you change the element itself. If you change the number of neutrons, you still have the same number of protons. It's still that same element. So this one is called helium-4 because it has 1, 2, 3, 4 in its nucleus. So helium-4. Okay, so how would I get helium-5, which is an isotope of helium? So to get helium-5, you can't change the number of protons because that changes the element itself. So for helium-5, you would have an extra neutron in there with a neutral charge. It doesn't change the charge of the molecule, and then you would call that helium-5. There's also an isotope helium-3. How would you get helium-3? So you would have to remove 2 of these neutrons, and then 1, 2, 3, and you would have helium-3. Okay, helium-3, so which one do you think of these would have the lower atomic mass? It would be helium-3 because you've actually removed a neutron, and a neutron has mass to it. And then helium-5 would actually have a greater atomic mass than just plain old helium-4, right? It's not a significant amount of mass difference, but there is a little bit of a difference. So there's more I want to talk about, but right now I'm going to stop this video. Unfortunately, I don't have the technology to be able to pause it and then keep going later. So if I stop it, I have to just stop the video. But you can go ahead and do the on your own questions and the example 3.1. Read through everything to get more detail about what I talked about, and then I'll talk to you about the really cool energy levels and the Bohr model next. So go ahead and make sure you do these. It's good practice.